Bismillah Rahman Rahim. So today we would be discussing our lecture 10, and the lecture 10 is actually about the forced vibrations. Up till now, we were discussing the free or natural vibrations, and in the free or natural vibrations, the disturbance, which is actually causing the vibration of the system or oscillation of the system, that is not present during the vibration of the system. It is not applying on the system during the vibrations, and the system vibrates at its own in the absence of the force of excitation. Simply, the force of excitation or disturbance is not present, and the system vibrates at its natural frequency. And in case of free vibration, natural vibration, we just discussed that as you disturb the system would vibrate at its natural frequency. We already discussed its equation of motion and the mathematical model for the response. In case of underdamped system, damped system, and overdamped system. In case of forced vibrations, actually the force of excitation would be always acting on the system during vibrations. The force of excitation would be actually responsible for the vibration of the system, and it would be always there during the whole vibration of the system. So such type of vibration is classified as forced vibration. And in this case, the system would vibrate at the frequency of excitation. In case of free or natural vibration, the system would vibrate at the natural frequency of the system. However, in case of forced vibrations, the system would vibrate at the frequency of excitation. Whatever is the frequency of the force of excitation, that would be the frequency of the vibration. And the response of the system would depend upon the nature of the excitation. By excitation, we means force of excitation. So we call it force of excitation or excitation function or simply excitation. And the displacement of the system is known as response of the system. So the nature of the vibration or response in this case would depend upon the nature of the excitation. If excitation is periodic, we are expecting that the response would be periodic. If the excitation is sinusoidal, we are expecting or the system response would be sinusoidal. If the excitation is random, the response would be random. Here you are seeing some examples of the forced vibration. The vibration of the washing machine. The source of vibration is actually the rotating drum, where we have an uneven mass of wet cloths and the belt and pulley and the motor. So it is vibrating. As long as the electric motor, which is actually used to drive this drum, it is operating, the vibration would be there. So this is an example of the forced vibration. Similarly, here in case of window type air conditioner and refrigerator, the real culprit is the sealed compressor, where we have a piston and cylinder arrangement rotary compressor. So as long as the electric motor, which is actually giving drive to the compressor, as long as that electric motor is operating, it is producing vibration, and that vibration is transmitted to the whole body of the air conditioner or refrigerator. So as long as that electric motor is operating, vibration would be there. So this is the case of forced vibration. Similarly, for this mixer, as long as the electric motor, which is used to drive the uh, given drive to these blades, so as long as that is operating, the vibration is there. Similarly, in automobile engine, the cause of vibration is the engine. In the engine, actually in the cylinder, combustion is taking place, which is pushing the piston during the expansion and compression strokes. So it is actually causing severe vibration of the engine. So as long as the engine is on and operating, there is severe vibration. There is vibration in the whole body of the automobile. As long as the vehicle is driving on the road, you would feel the vibration inside the passenger cable. As long as the aircraft is engines are on and it is actually flying, the passenger would feel the vibration. So all these are examples of the forced vibration. Similarly, here you see an electrical generator which is coupled to the steam turbine. So as long as the steam turbine is operating or the electric generator rotor is rotating, the vibration would be there. So these are all examples of force vibration. So force vibration exists in reality. So we have to model uh, these systems in order to find out the response or the level of vibration and how to control that level of vibration in these systems. So for that, as we know that in order to know the behavior of the vibratory system, we have to model our system. And the easiest model is actually the lump parameter model. The lump parameter model means that we have our real model, our real system has mass, so we have to take all of the mass on one side, which would be m, all of the elasticity in the spring, and all of the energy losses in the damper. So we could model our system as lump parameter model. And in the lump parameter model, the simplest model is actually the 1 degree of freedom model. So initially we would model our system, these vibrating system, as single degree of freedom system for the sake of simplicity. It also depends upon the requirement. If the requirement is to find out the fundamental frequency, so the easiest way is to model your system as 1 degree of freedom system, because this is the easiest model or simplest model. If the requirement is to find out the two natural frequencies, that then in that case you have to model your system as 2 degree of freedom system. So here, for the sake of simplicity and learning, let's say we are modeling our actual systems, which are real systems which have multi-degree of freedom system. We are modeling them as 1 degree of freedom system. So let's say this is the mass of the system, elasticity of the system, and the energy losses, that is damping in the system. This is the forcing function or force of excitation or simply excitation, and this is the response of the system. In order to develop the equation of motion, so I have to draw the free body diagram for it. So here you see the mass. Let's say that at this instance, let's the mass is moving in the upward direction. So the spring would extend. So if it extends, so it would pull the mass in the downward direction. So the spring force would be in the downward direction, that is opposite to the motion at that instance, and the magnitude is kx, whereas the damping force is always opposite to the displacement. So if the displacement is at this instance in the upward direction, so the damping force would be in the downward direction. So here the damping force is cx dot, it is in the downward direction. The forcing function is in the upward direction, the displacement is there, and the weight is acting in the downward direction, mg, and this is actually the force due to static deflection. And we already discussed that the spring force due to static deflection would be balanced by the weight of the mass. So these would be equal in magnitude but opposite in direction. So they would cancel out in the equation of motion. Here I am showing that, but in further analysis or further lectures, we would be not showing the mass, that is, sorry, weight, and the spring force due to static deflection, because it is already understood that these two are there, but they are opposite in direction and they would cancel each other. So there is no need of including them. And secondly, the x coordinate which we are showing here, it is already understood that we are taking this x from the equilibrium position of the system, not from the unstretched position of the spring. So we are assuming this x from the equilibrium position. So in that case, these two would cancel out. So writing the equation of motion while using the Newton's second law of motion, which is actually the summation of all of the forces is equal to the uh, inertia force, that is mx double dot. So using the Newton's second law of motion, which is mx double dot, and it is equal to the summation of all of the forces, sigma f along displacement. So here what we have this spring force, and it is opposite to displacement, and all those forces which are opposite to the displacement, all those forces which are opposite to this displacement, we have to take negative. So minus kx, damping force is also opposite to the displacement, so minus cx dot, and the force of excitation is along the displacement, so plus f of t. And I'm not including the weight and the spring force due to static deflection because they are equal and opposite to each other, so they would cancel out with each other. So after rearranging the equation, we would have mx double dot plus cx dot plus kx is equal to 0. So we have a differential equation, ordinary differential equation. Why we have an ordinary differential equation? Because here x is a function of time only. X is the dependent variable. X is a function of time only. X is the dependent variable and t is independent variable. So here we have only one independent variable. So we would have actually ordinary differential equation. So this is an ordinary differential equation. Here on this side we have a forcing function. So we don't have a zero here. So we have non-homogeneous ordinary differential equation. Also x double dot, x dot, and x1, the power of these is 1, so we have a linear differential equation. Also these are constants, c is constant, m is constant, k is constant, so we have a second order because there are two DAs, so we have second order ordinary linear uh, non-homogeneous differential equation with constant coefficients. The response of such a system, that is in case of forced vibration, actually as we discussed, that depends upon the nature of the force of excitation. If the force of excitation is sinusoidal, then the response would be sinusoidal. If the force of excitation is periodic but not sinusoidal, so the response would be periodic and it would be not sinusoidal. If the force of excitation is random, then the response of the system would be also random. If the force of excitation is transient, that is only for some time, and then there is no force of excitation, then the response would be what we would have. The response actually then in that case depends upon whether the system is overdamped, underdamped, or critical damped. But the response of the system in that case would be just like the uh, free vibration or natural vibration. So for underdamped system, we would have vibration and we have amplitudes, but the amplitude of vibration would be decreasing with the passage of time, and after some time we would have no vibration. In case of overdamped system, there would be disturbance and then the system would reach to the equilibrium position without vibration. In the case of critical damp system, the system would reach the system would there would be a deflection, but then the system would reach to the equilibrium system in the minimum time without vibration. So we have the ordinary differential equation non-homogeneous. We have a non-homogeneous differential equation here. the forcing function, let's say the force of excitation is periodic and sinusoidal, then mathematically we could write down this as f of t is equal to f naught cos omega t. So our equation of motion would become mx double dot plus cx dot plus kx is equal to f naught cos omega t. For the sake of simplicity, or just for those systems where the damping, that is the energy losses, are very very small, so and ignorable, so we are putting c, that is the damping coefficient, as 0. So putting c is equal to 0 here, then we would have the equation of motion mx double dot plus kx is equal to f naught cos omega t. So this is the equation of motion for undamped system which is subjected to forced vibration. We have a non-homogeneous differential equation. So in mathematics, you have already studied that for the non-homogeneous differential equation would have two solutions. One part of the general solution, this is the general solution. It is known as the homogeneous solution, whereas the other part is known as particular solution. Homogeneous solution is actually the part of the, it is actually the solution of the corresponding uh, corresponding differential equation. So what is the corresponding homogeneous differential equation, homogeneous differential equation for this non-homogeneous differential equation? You have to just put it 0. So the corresponding homogeneous differential equation for this non-homogeneous differential equation is mx double dot plus kx is equal to 0. So this homogeneous part we could find out from this homogeneous differential equation. In vibration, the general solution, this general solution, we call it the total response of the system. X of t is the total response of the system, and the homogeneous response is actually called the transient response, whereas the particular solution is known as the steady state solution. So here in vibration, the total response of the system would be the combination of the transient response and the steady state response. This homogeneous part, that is the transient part, we could find out from this corresponding uh, homogeneous differential equation. So x transient is the solution of the corresponding homogeneous differential equation. And if we look at the equation, this is the equation for free vibration system. So once we have a natural vibration or free vibration, then for that system, the equation of motion would be a homogeneous differential equation. And we have already discussed this. And in case of underdamped system, where zeta is less than 1, there would be vibration, and the response, that is the x transient of time, could be mathematically modeled as a cos omega nt plus b sine omega nt. In case of free or natural vibration, the system would vibrate at the natural frequency. So here in this mathematical model of the response, we have to write omega n. And a and b are arbitrary constants, and in order to find these arbitrary constants, you have to use the initial conditions. And if we plot this transient response, then it would be sinusoidal and periodic. This is the time period. Along the vertical, we have the x transient of time, and along the horizontal, we have time. So we, for the total response of the system, we already know the transient response of the system because we have already studied and we have already modeled it. The steady state response, the system is vibrating if the forcing function or the force of excitation is periodic and sinusoidal. So we are expecting that the response would be also sinusoidal. So if we are modeling the steady state response x s of t, so it would be also periodic. So it would be capital X cos omega t, where capital X is the amplitude. It is the amplitude of the steady state response. So if this is the solution of the differential equation, if this is the solution of this differential equation, so this must satisfy this differential equation. So we have to put for x and x double dot in the equation. So differentiating our response once, so we would get x dot, which is minus omega x sine omega t, and we would get x double dot after differentiating this again with respect to time, minus omega square x cos omega t, and putting for x and x dot in our differential equation, uh, we would have this equation m minus m omega square capital X cos omega t plus kx cos omega t is equal to f naught cos omega t. Now here we could take x cos omega t common. So x cos omega t we are taking common. So inside the parenthesis we have minus m omega square plus k. Here we have cos omega t, here we have cos omega t. This is the coefficient of this cos omega t, and here we have the coefficient of the cos omega t on the other side is this. If these two are equal, if these two identities are equal in the equation, so what does it mean? That the coefficient of cos omega t are equal. So equating the coefficient of cos omega t on both sides of the equation, we could write down that m minus m omega square plus k x is equal to f naught, and in the equation there is capital X. What we are doing, we are actually, if you look at this equation, omega is the frequency of excitation. We could find it out very easily. It could be given, or we in the beforehand we would know the value, or if you don't know the value, simply we could measure the frequency of excitation very easy. That is not a problem. So meaning that in this steady state response we know frequency of the excitation. The only unknown is capital X, the amplitude of the steady state response. Once this amplitude is known, then we would be in the position to know the steady state response. So we are trying to find out this capital X. So here this equation is telling us that this quantity which have capital X, it is equal to F naught. And from there we could find out capital X. So if we divide by this quantity here, then from the equation we would have capital X is equal to F naught by k minus m omega square. So this is the amplitude. Now we have the amplitude of the steady state response in terms of the system parameters, that is stiffness and mass and frequency of excitation and the amplitude of the excitation. So X steady state at t is equal to f naught k minus m omega square cos omega t. So this is actually the steady state response. We could plot both of the responses together. The blue line represents the steady transient response. It is representing the transient response, which is at the natural frequency of the system, whereas the red line represents the steady state response. And while combining these two signals, while adding these two signals here, you are seeing the total response of the system, that is x of t. So in this case, this would be the total response of the system. So the total response of the system, it is the summation of the transient response, which is A cos omega nt plus B sine omega nt plus f naught by, this is the steady state response, f naught by k minus m omega square cos omega t. And in order to find out the arbitrary constants a and b, we could use the initial condition. So utilizing the first initial condition, that is x of 0. So in this equation I am putting t is equal to 0. So cos 0 is 1. So I would have a, and that a is written here. And sine 0 is 0. So b, this quantity would be 0. Here again cos 0 would be 1. So we would be left out with this quantity. So x of 0 is equal to a plus f naught k minus m omega square, and from there we could find out the capital A as x of 0 minus f naught k minus m omega square. And in order to find out the second arbitrary constant b, so first you have to differentiate this equation. So differentiating this equation with respect to time, we would have the differential of cos omega nt would be sine omega t 1t minus sine omega minus sine omega nt. So minus is written here, cos omega nt is written here, and then it would uh, differentiate the argument, and from there we would get omega n plus sine omega nt, so cos omega nt with omega 1 omega n, and minus x omega x, for this I'm writing x, and then sine omega t and omega, and then utilizing the initial condition, second initial condition, that x dot of 0 is equal to omega n. So x dot of 0, so this would become 0 and this would become 0. We would be left only with this component. So b omega n, and this is 1. So x dot of 0 is equal to omega n b. And from there b is equal to x dot of 0 omega n. So putting for the arbitrary constants in terms of the initial conditions, the total response of the system would be x of 0 minus f naught by k minus m omega square cos omega nt plus x dot of 0 by omega n sine omega nt plus f naught by k minus m omega square cos omega nt. So this would be the total response of the system. So further analyzing the mathematical model that we have developed for the amplitude of the steady state response, which is f naught by k minus m omega square. And if we look here, it actually depends upon the frequency of excitation. We would just rewrite this equation. What I'm doing here, I'm dividing this I'm dividing this quantity by m and multiplying with, sorry, I'm multiplying and dividing this by k. So let's divide and multiply that quantity in the numerator by k. So I'm writing k here, multiplying that quantity by k and dividing that quantity by k. So m by k, omega n square is equal to what? It is equal to k by m, and m by k is the inverse of that thing, so it is 1 over omega n square. So meaning that this m by k is 1 over omega n square, which is written here. So we have rewrite the same equation in a different way in order to make our analysis easy. So the amplitude of the steady state response is written here, f naught by k minus k omega square by omega n square. This is the frequency ratio. So if the amplitude of the steady state response actually depends upon the value of frequency of excitation. So if omega is too small than omega n, if this quantity omega is too small, then omega n, in other words, omega n is too large as compared to this omega. So what if we divide a smaller quantity with a much bigger quantity? So the final value would be approximately equal to 0. It would be very near to 0. So in that case, this value would be near to 0. So meaning that from k we are subtracting approximately, we are subtracting approximately nothing. So approximately this quantity would be f naught by k, and f naught by k is known as the static deflection. It is known as static deflection. So what does that mean? It means that if the frequency of excitation is too small than the natural frequency of the system, in that case the amplitude of the steady state response would be equal to the static deflection. It would be equal to f naught by k. So it is a very important conclusion. So knowing the knowledge, the model, the mathematical model, if you look at the mathematical model, the beauty of the model is that within seconds it will give you the results without any experiments, without doing any complicated derivation and calculation. Very simply, because now we know that the model is actually telling us that if the frequency of excitation is too small than the natural frequency of the system, in that case the amplitude of the steady state response would be f naught by k, which is the static deflection. So if somebody asks you that what would be the amplitude of the steady state response, so you must have to ask only one question, and that question would be what is the frequency of excitation and what is the natural frequency of the system. So if you know that the frequency of excitation is too small than the natural frequency of the system, so simply tell to them that in that case the amplitude of the steady state response would be equal to f naught by k. So within second you would calculate, you would know f naught, you would know the stiffness of the system. Within 1 second you would just do the calculation and you have to tell him that this would be the amplitude in this case. Second case, if omega, the frequency of excitation, is too large than the natural frequency of the system. So now in this case, this quantity, let's say this quantity is too large. This is too large in comparison to this quantity. So this quantity would be dominant. This quantity would be dominant, meaning that this quantity would be too large. And if you look here, this quantity has a negative sign. So this quantity, the denominator would carry the negative sign, and we are writing the negative sign here. So approximately in that case, the amplitude would be minus f naught, and this quantity would be dominant in comparison to this k. So we are writing that quantity here only with this approximation sign k omega square by omega n square with negative sign. So what does that mean? It means that if the frequency of excitation is too large than the natural frequency of the system, then actually the amplitude of the steady state response would be calculated by this, but there would be also a negative sign, and that negative sign means that in this case the response would be out of phase the excitation, both would be out of phase. Here, actually, we have a positive sign. Here we have a positive sign. What does that mean? It means that both the signal would be in phase. The peaks of both would appear at the same time. Here, the if the peak of forcing function is appearing, so on the other side, that is, in case of response, we would be seeing the opposite. That is, if you are seeing the crest of the force of excitation, we would be seeing the trough of the response. So both the signal would be out of phase because it is clearly you could see a negative sign. So both the signal would be out of phase. Third case is if omega is equal to omega n, when the frequency of excitation is equal to the natural frequency of the system. That is the case of resonance. So in that case, if we put omega by omega n is equal to 1, both are equal, they would cancel with each other, and then we would have k minus k. And here we would have 0. So f naught by 0. And mathematically, we describe this as infinity. So the mathematics actually tells us that in that case, when omega is equal to omega n, the amplitude of the steady state response would be infinity. What does that mean? If we interpret that, it means that actually the system would violently vibrate and the mass would move and it would go and it would pass through sky and it would reach the one end of the universe, and from there it would come back, it would pass through the equilibrium position and it would reach the other end of the universe. If this is the interpretation, then it means that in that case actually the system would destroy and we would have no system at the resonance. But actually that is not the case physically. Physically, at resonance, we would have a violent vibration. The amplitude of the vibration would be maximum, but it would be not infinity. So what is actually the problem? Where is the problem? So actually the problem is in the model, this mathematical model. This mathematical model works fine when omega is more than omega n. It works fine when omega is less than omega n. It is actually calculating the accurate values, approximately accurate values or good results when omega is less than omega n, when omega is larger than omega n. It is actually giving us the exact values of the displacement or amplitude of the steady state response. However, at this particular point when omega is omega n, it is not capable to exactly calculate the amplitude of the steady state response. So this is actually the limitation of this model. It is actually telling us that something would happen, and the response of the system would be maximum, but I am not capable to exactly calculate what would be the amplitude at the resonance. So the problem is actually in this model. The problem is not in actual system. We know that at resonance the actual system would violently vibrate, and but that vibration would have a certain amplitude. It would be maximum, but it would be not like that the mass would be moving violently, and it would be the amplitude would be infinity. So the problem is in the model. So just for the sake of mathematics, because here the mathematics is telling us that the amplitude would become infinity, so we could model our response as x of t is equal to f naught omega n t by 2k sine omega n t. So here you could see that in the amplitude we have put t time. So with the passage of time, this amplitude is the function of time. So if we simulate this, so with the passage of time, the amplitude of vibration would increase, and when time is equal to infinity, the amplitude would become infinity. So let's discuss some examples. So let's say if we have a spring mass system, the mass suspended mass is 10 kilogram, the stiffness of the spring is 1000 Newton per meter, and the force of excitation F of t is equal to 100 cos omega t. So we have developed the model. So this is the model for the steady state response f naught by k minus m omega square cos omega t. Here omega n is equal to k by m. K is 1000 and m is 10. It is 10 radians per second. So now plugging for f naught, which is here 100, k 1000, which is here, and m 10. So we have this mathematical model for the steady state response. So case 1, if omega is less than omega n. Let's say if f of t is equal to 100 cos 40. 4 is actually the frequency of excitation, and the natural frequency is 10 radians per second. So meaning that the frequency of excitation is less than the natural frequency. So in that case, if we plug the values, for omega, which is 4, so 4 square is 16. uh, and then if we do calculation, then after calculation, the steady state response would be 100 by 840 cos 40. So if we look at the force of excitation, plus sign here and also plus sign here, what does that mean? It means that in this case, both of the signals would be in phase. Here the amplitude is 100, but here the amplitude would be 100 by 840. And this would be the frequency of excitation, this would be the frequency of response. The system would vibrate at the frequency of the excitation. So the plot of the forcing function and the plot of the response, both of the peaks would appear at the same time, both of the trough would appear at the same time, meaning that both of the forcing function and the response would be in phase. Second case, if omega is larger than omega n. So in this case, let's say the frequency of excitation is 20. So f of t is equal to 100 cos 20t. So again, if we go back, here, we have to put omega as 20. 20 square is 400. 400 into 10 is 4000. And if we do the calculation again here, so we would get x steady state with minus sign 100 by 3000 cos 20t. So if we compare these two mathematical models here, so here we have plus sign, here we have minus sign. The amplitude is 100, the amplitude is 100 by 3000. And here we have a negative sign, both cos functions. So negative sign means that these two would be out of phase with each other. The response would be out of phase the force of excitation. If we are seeing crest here, so we would be seeing the trough here. If it is positive, this would be negative. If this is negative, this would be the positive. Third case, if omega is equal to omega n, that is resonance. So f of t is equal to 100 cos 10t, and in this case we have to use the other mathematical model, that is x of t is equal to f naught omega nt 2k. We have to plug the values in this equation. So x ss of t is equal to 1000 t by 2000 sine 10t. And if we simulate this equation, so here you see that both of the signals would be in phase, plus sign here, plus sign here, both of the signals would be in phase, but here the amplitude is the function of time. So the amplitude of vibration would increase with time, and as the time tends to infinity, the amplitude of the steady state response would tends to infinity. That actually the model is telling us. In reality, that would be not the case. At resonance, we would have a violent vibration. The amplitude of vibration would be a maximum, but it would have a measurable range. It would be not infinity. The problem, as we discussed earlier, that the problem is in the model. The model is actually giving us the exact values at omega greater than omega n or omega less than omega n. But at this particular value, when omega is equal to omega n, the model is not capable to give us the exact value or actually calculate us the exact value, but it is just telling us that something is happening at this particular point, but I am not capable to actually calculate the exact value for you.